Let's talk about inverse function. So we need to review a few things first. When we talk about a function is a very special kind of relationship. We said each x value corresponds to only one y value. And we said back in that first unit that we could tell whether we have a function by using that vertical line test. Well, now we need to talk about the definition of one-to-one. So one-to-one is kind of the opposite in a way. Now, instead of each x going to one y, we want each y to go to only one x. And to tell whether or not something is one-to-one, we can use a horizontal line test. Horizontal line test works the same way. If we have a graph of a function, maybe it looks like this, we're using horizontal lines. So does that line cross the graph more than one time? And in this case it does, so this guy would be not one-to-one. And I'm going to abbreviate one-to-one that way. Now, if we have a function that is also one-to-one, okay, that means it passes both the vertical and the horizontal line test. Then that's very special because it's going to have an inverse. So keep that in mind. It's got to be a function in one-to-one, so it must pass both of these. So the notation we're going to use for an inverse, how do we know we're dealing with an inverse? Well, we're going to see this kind of notation. That -1 looks like it's an exponent. It is not an exponent. It's just the notation we use for a one-to-one function. So let's talk first about verifying inverses. If we have a function and we have its inverse, and we were to form composites, then we're going to get x. This is that case we talked about in the last section. Well, if we take a function and we form the composite with itself, or we do it in the opposite way, we get the same thing. And that same thing will always be x. You do have to check it both ways. Otherwise, you may not have inverses. It's very possible. That way may give you x. This way may give you something different. So you always have to check both. So let's walk through a few examples. I'm going to write these on the next page. Let's look at 33. We want to verify these guys are inverses. So let's form some composite functions, f of g of x. So if I take f of x, which is 3x plus 4, and I substitute in that g of x. Now let's work this out. We have 3 times 1/3, so those are going to cancel, and we have x minus 4 plus 4. Do you see how that one gives us x? Now let's do this in the opposite order. Let's look at g of f of x. Our g function is 1/3 times x minus 4. Now I'm going to substitute in 3x plus 4. Order of operations, I have to deal with that inside first. 4 minus 4 cancels. 1/3 times 3x is x. So you see how we're getting x both ways here. This is a way for us to verify the inverses. Now we're going to talk about domains of these two. So let's talk about the domain of f. This guy's the equation of the line, so we can substitute anything in for that domain. If we look at g, we can substitute anything in for that one. That one's just another line. So those domains are going to be all real numbers. What we're going to discover in a minute is that there's going to be a very special relationship between domains and ranges. Let's look at 37. 37, we have f of x is equal to x cubed minus 8. G of x is equal to the cube root of x plus 8. We want to verify these are inverses. So let's form some composites. F is x cubed minus 8. And we're going to substitute in that cube root of x plus 8. So you can see how cubing a cube root will leave us with just the radicand. And then 8 minus 8 cancels. So we get x. If we do it the other way, we have the cube root of x plus 8. We're going to substitute in x cubed minus 8. Negative 8 plus 8 cancels. And if I take the cube root of x cubed, I'm going to get x. So you can see how we're getting the same thing both ways. Domain, this one's not going to be very interesting either. This is the cube root function shifted down 8 units. So if we think about what that guy looks like, it's going to look something like this. The domain is going to be all real numbers. If you think about your g function, that's the cube root of x shifted to the left 8 units. So that cube root function is going to look like that. That domain is going to be all real numbers too. Let's look at the next one. This one's going to be very interesting. Let's look at 41. We have f of x is equal to 2x plus 3 over x plus 4. G of x is equal to 4x minus 3 over 2 minus x. Let's form those composites first. Let's verify these guys are inverses. So we have 2x plus 3 over x plus 4. We are going to substitute in 4x minus 3 over 2 minus x. So I'm going to use that trick in just a minute. I'm going to go ahead and distribute that 2 to that top. So now let's use that trick. Let's multiply by that least common denominator, which is 2 minus x. So that's going to cancel with this. So we're going to have 8x minus 6. But that second term, that 3, is going to be multiplied by that 2 minus x. Same thing here. When I multiply that fraction by that 2 minus x, it's going to cancel that denominator. So we're left with just the top of the fraction. But that 4 has to be multiplied by 2 minus x. So we have 8x minus 6 plus 6 minus 3x over 4x minus 3 plus 8 minus 4x. I'm going to simplify. So we have 5x in the top. You can see those cancel in the bottom. So we just have a bottom of 5. And that reduces the x. Now let's go the other way. G of f of x. So our g function is 4x minus 3 over 2 minus x. And we are going to substitute in 2x plus 3 over x plus 4. So I'm going to go ahead and distribute that 4 to the top of that fraction. 8x plus 12 over x plus 4, and then minus 3 over 2 minus, this is 2x plus 3 over x plus 4. Let's multiply by that least common denominator. Multiplying this fraction by that will cancel that denominator. So we have 8x plus 12 here. And then when we distribute this to that negative 3, it's going to be negative 3 times x plus 4. When we distribute this x minus 4 to that 2, it's going to be 2 times x plus 4. And then we have that minus. And then when I distribute this to this, it's going to cancel that denominator. That minus is going to have to go through that numerator that's left over. So I'm going to put that in parentheses. Be very careful on that. So let's distribute. So now let's look at what cancels. We can see those 12s are going to cancel in the top. So we're going to have a 5x in the top. That is completely coincidental from the 5x in the top of the other one. In the bottom, the 2x's cancel and we're left with a 5. 5x divided by 5 is going to be x. So you can see how we're getting x both ways. So that's how we verify we have an inverse. So now I want to analyze these a little bit more. Let's look at the domain of f. What kind of numbers do we have to leave out here? Well, we don't want that bottom to be 0, so it looks like we're going to have to leave out a negative 4. Let's look at our g function. What do we have to leave out here? In this case, we're going to have to leave out a 2 because 2 would make that denominator 0. Now, I want to analyze this a little bit further just for fun. Let's look at vertical asymptotes. That vertical asymptote for that first one would happen at x equals negative 4. What about for our g function? I'm going to write it that way. I'm going to rewrite this one so we know it's for f. So let's look at that g function. That vertical asymptote would happen at 2. Now let's look at the horizontal asymptote. If we were to look at the horizontal asymptote, the degree of the top and the bottom is the same. So it's the ratio of the leading coefficients. So it's going to be 2 over 1, which is 2. If we look at the horizontal asymptote for that second function, okay, the ratio of the leading coefficients would be 4 over negative 1, which is negative 4. So you should see something pretty interesting happen here. Check this out. If we look at the f function and we look at the g function, this guy is a g. Check out that change. We had a vertical asymptote in negative 4 in f, and then we had a horizontal asymptote in g at negative 4. Y equals a negative 4. So those numbers are the same. Check out what happens here. So we're going to see that same kind of relationship there. And in fact, we could even talk about the ranges of f and g. And it turns out the relationship's pretty interesting. What's going to happen here is that the range of f ends up being the domain of g. So if we leave a 2 out of g for the domain, then we're going to have to leave it out of the range of f because these guys are inverse functions. And if we look at the range of g, well, the range of g happens to be the domain of f, so we would leave a negative 4 out here. So let's talk about these relationships. Talk about this just a little bit more in depth. So those domains and those ranges are going to flip. The domain of f ends up being the range of the inverse. And the range of f ends up being the domain of the inverse. So those x's and those y's end up switching. If we have horizontal asymptotes and vertical asymptotes, they switch too. The horizontal asymptote of f ends up going to the vertical asymptote of G. The vertical asymptote of F ends up becoming a horizontal asymptote of G. Another thing is the graphs. If we graph F and F inverse, then they're going to be symmetric. About the line y equals x, which means if we were to graph that function along y equals x, we would see that kind of symmetry come out of that. And then that last one just has to do with the composite functions. If we take f and form the composite with f inverse, or we do it in the opposite direction, we're always going to get x. So I kind of want to show you this relationship with a couple of these graphs. So we're going to go to Desmos to graph these. So let's go back to number 37, where we have f of x is equal to x cubed minus 8. So that's that red graph that we see here. And then we had the cube root of x plus 8, which is that blue graph. So you can kind of see that symmetry coming out. If we were to graph that line y equals x, there's that green line. If we were to fold this graph along that green line, you can see how that top and that bottom would just match up perfectly. That's what we mean when we talk about symmetry about the line y equals x, is that if we were to fold it along that graph, those two pieces would line up along that fold. Now, let's look at number 41. So if we graph f of x, there's our f of x function. I'm going to zoom out just a little bit. So we can see that vertical asymptote would happen in here at -4. You could see the horizontal asymptote, and we could graph those if we wanted to. You can also see that domain restriction at -4. I'm just going to pop that in so you can see that. So there's our vertical asymptote for that one. And then our horizontal asymptote would be at y equals 2. Oops. So there's that horizontal asymptote. So you can see those asymptotes. You can also see that domain is everything but -4, and that range is everything but 2, because that graph's just not crossing that horizontal asymptote there. So we can see all that domain information and range information that we came up with over here for that f of x function. Now let's analyze that g of x function in Desmos also, so you can see that. So I'm going to delete those guys. There's my g of x function. So we said we had a vertical asymptote at 2, x equals 2. So there's that vertical asymptote, that green line. And we had a horizontal at y equals -4. So there's that horizontal. We know the domain would be everything but 2. The range would be everything but -4. That's the same thing that we said over here when we were analyzing that g of x function. So the graph matches up with everything that we said here. And what we're really trying to do, what I'm trying to get you to see, are all these relationships, how those asymptotes flip from f to g, or f to f inverse. I'm going to use that f inverse notation here, just so I'm consistent. I want you to see that symmetry about the line y equals x, and I want you to see how that domain and range is changing. So now I'm going to delete those asymptotes, and I'm going to graph both of these on top of the same plane. So you can see that purple graph was our f, or that black one is our g. If we were to graph the line y equals x, you're going to see that symmetry come out. If we were to fold this graph along y equals x, that top and that bottom half is going to match up perfectly. So we do have symmetry about the line y equals x for these. So you can see all those pieces that we were talking about coming out all those relationships coming out of not only this example, but that easier example we had before. So now that we've verified all that, now that we know this, and this is your key really to a lot of this section, understanding those relationships. What I want to do is play a little bit more with this idea of one-on-one, one-to-one. So we want to know, are these going to be one-to-one? And the easiest way to tell is to use that horizontal line test. So that's what we're really going to focus on here. If we were to look at these points, one-to-one, remember, means each y goes to only one x. So let's graph them. If you're not sure, you can always graph the points. So if we were to graph number 15, we have a point at 2, 6. At negative 3, 6. At 4, 9. And then at 1, 10. And this is 6 there. So you can see right off the bat there's an issue here. And the reason is that y value is going to 2 different x values. So this guy's definitely not one-to-one. Now, it does pass the vertical line test. So it is a function. But because it's not the one, it's not one-to-one, it does not have an inverse. Let's look at that next one. Let's analyze those y values. We have different y values here. So since they're different y values, this guy is going to be one-to-one. Notice the x values are different too. And since those x values are also unique, then it's definitely a function. And because it's one-to-one and a function, it will have an inverse. Let's look at 19. Okay, this guy passes the horizontal line test, so it's one-to-one. Okay, every horizontal line I draw would only touch that graph one time. That's what it means to be one-to-one. Each y goes to one x. Now, it also passes that vertical line test, so it's also a function. So we're going to kind of analyze this a little bit further than the directions say. So it's one-to-one, it's a function. That means it will have an inverse. And we'll talk about how to find the inverse in a little bit. Let's look at 20. 20 passes that horizontal line test, so it's one-to-one. It passes the vertical line test, so it's a function. So then it will also have an inverse. What about 21? 21, if we were to look at horizontal lines, this y value corresponds to 2 different x values. So this is not one-to-one. Okay, it is a function. It passes the vertical line test. But because it's not not one-to-one, it will not have an inverse. (22) is going to kind of be in the same boat. Those y values are corresponding to 2 different x values. This y value of 2 has 2 different x values here. So this is not one-to-one. It is a function. It passes the vertical line test. But because it's not one-to-one, it does not meet all the criteria. So it will not have an inverse. (23) is one-to-one. Passes the horizontal line test. It's the function. It passes the vertical line test. Then that means it will have an inverse. 24 is not one-to-one. This guy's just a horizontal line, so every point on this line actually ends up being a problem. Okay, but it is a function. It does pass that vertical line test, but because it's not one-to-one, it will not have an inverse. So, what if we have something that is one-to-one? How do you find the inverse function? And it's really easy. It just depends on kind of what you have. You're always just going to switch x and y. If you have a set of points, then you literally just switch the x with the y value. You have a new set of points. There's your inverse function. If you have an equation, you literally switch x and y. You solve that new equation for y. That's your inverse function. It's always about switching x and y. And that's really why your domain of f is the range of the inverse function, because you're literally switching that x and y so that you do have that symmetry about the line y equals x. So that's why those domains switch, because that's how we find that equation. There's the parallels between the domain and range versus finding that function and what that is going to look like. Okay, but it does have to be one-to-one. It does have to have an inverse function. So if we look at this guy, we have a set of 4 points here. I'm going to list those points out. I'm just going to call it f of x. So we have the point 1, 2, 0, 1, negative 1, 0, and negative 2, negative 2. Okay, this guy is a function. It passes the vertical line test. This guy's a one-to-one. It passes the horizontal line test. Remember, we're just looking at this blue piece. That y equals x is just there for us for symmetry later. So because it's a function, because it's one-to-one, it's guaranteed to have an inverse. So to find the inverse function, we are literally going to switch the x and y coordinates for each ordered pair. So the x coordinate's 1, the y coordinate's 2. Our new point on the inverse is going to be 2, 1. The point 0, 1 is going to change to 1, 0. The point negative 1, 0 is going to change to 0, negative 1. The point negative 2, negative 2 would change to negative 2, negative 2. So that's our inverse function. It's just a set of points. Now, let's graph those. You should see that symmetry about y equals x. Our first point is the point 2, 1. Over 2 up 1, there it is. Then we have the point 1, 0. Over 1 up 0. We have the point 0, negative 1. Just down here. And then the point negative 2, negative 2 is here. And if we connect these dots, there's our graph. So this is our inverse function. And you can see how it has symmetry about the line y equals x. If we were to fold this graph along this line, this would line up with this guy. So it's pretty cool how that works. Now let's look at equations. We have 51, that's 4x plus 2. We want to find the inverse function. Now, this guy is one-to-one. This guy is also a function. As the line is increasing, so we can see that it meets the criteria. So to find the inverse function, we are literally going to switch x and y. So we're going to rewrite this as x equals 4y plus 2. And then we're going to solve this new equation for y. So let's subtract 2. And then let's divide it by 4. So there's our inverse function. So I'm going to use that proper notation here. And we could rewrite that as x over 4 minus 2 over 4. Just to clean it up, this is 1/4 x minus 1/2. I would like to see it that way. So there's our inverse. I'm going to write this a little bit neater down here. If we were to graph this guy, with the original, you're going to see that symmetry about the line y equals x. You should take some time, pull your calculator out, pull Desmos out, and graph that just so you can see those relationships about the symmetry and domains and range and all that fun stuff. Let's look at 55. So this is x squared plus 4. Okay, but keep in mind, we're only looking at part of that graph. X squared plus 4 is a transformation of x squared. It's shifted up 4 units. And we only want the right half of the graph because they've restricted the domain here. It passes the vertical line test and the horizontal line test. It's 1-to-1. It's a function. It's guaranteed to have an inverse. So to find the inverse function, we are going to switch x and y. And then we're going to solve this for y. So we're going to subtract 4. And then we're going to take the square root. Remember, anytime you choose to take the square root, you have to put the plus and minus. So here's the problem. It can't be both of these, because both of these would be a sideways quadratic. It can only be one. So we've got to figure out which one. So let's analyze a little bit. We know the domain of the original function is all x values bigger than or equal to 0. And we know that because they gave that to us. We also know the range of this function. Just for fun, let's find that. This graph would look like this. Remember, transformation of x squared shifted up 4 units. So that smallest y value is going to be 4. And this guy's going to head to infinity. So if we know the domain and range of f, then we know the domain and the range of f inverse. And that will tell us which one of these we need to use. Is it the positive or the negative? I'm going to rewrite this in interval notation. We're going to go from 0 to infinity here. So we know the domain of f is the range of the inverse function. So that's going to go from 0 to infinity. We know the domain of the inverse ends up being the range of the original. So from 4 to infinity. So keep in mind, we're talking about outputs here. So we're talking about the range of the inverse. We want these to be positive numbers. That means we have to use the positive value here. So that inverse function is going to be the positive square root of x minus 4. And we could also verify that using Desmos again, because this guy has to be symmetric about the line y equals x. If we were to graph that square root of x minus 4, it's going to look like this. So we would see that symmetry about that line. If we graph the negative is not going to give us the symmetry that we need, because remember, that's going to be a reflection. So it would be that red one, or that red graph there, dotted one. And that's just not going to give us that symmetry. So you can verify it in a couple of ways. You can use that relationship between domain and range, or you can use that idea about symmetry to figure out, do I need the plus or the minus? And then let's look at that last one, 63. Let's find that inverse function. So we are going to switch x and y. And then we're going to solve that guy for y. So to solve for y, we're going to multiply both sides by the y plus 2. I'm going to distribute. So to solve this for y, we need the y terms on the same side. Let's move this guy to the left, to the right, by subtracting. So now we have that. And if you notice, both of the terms on the right have a y in common. So we can pull it out. And then we can divide both sides by that 3 minus x. So there's our inverse function.